Start.
Yeah. As soon as everyone's ready. Yeah, you can go whenever you want.
So I think I'll get started. So, hello everyone. Thank you for showing up. The very first node of the year. Of this fall. Session, whatever. So this was my talk for EMNLP months ago, and the title is Filling the Blanks for Mad Libs Humor. And this was a work in collaboration with Microsoft Research. Actually, when I was an intern there, that's where we started this project. And so I'm going to talk about that. So these are actually Mad Libs. Maybe some of you have already seen it, but I'll go to them in details. So here is one Mad Lib, like part of a Mad Lib. So Mad Libs are stories that have words, words that have been replaced with blanks, and you have certain hint types, and you have a title. So it's like a description of something. So for example, this is a description of the Mona Lisa. So and so here the story is Mona Lisa is a blank 16th century portrait painted in a liquid by Leonardo da Vinci. So you use the hint to put a word. So, for example, this was the original story. Mona Lisa is a famous 16th century portrait painted in oil, which is the liquid by Leonardo da Vinci, and many people think Mona Lisa's smile is mysterious. So now, so this is a Mad Lib version now. Now, here, the player who's playing the game is going to put in words to make the story funny. And so one way of doing it is something like this. So if you do like Mona Lisa is a hilarious 16th century portrait painted in lemonade by Leonardo da Vinci, and then you can say many people think that Mona Lisa's gender is mysterious, for example. So and you can see the humor coming out here. So I've replaced some original words with words that make funny given the context. And so what's actually happening here is the incongruity theory of humor, which says that unexpected or surprising word or concept that still fits the sentence can generate humor. So if you have a surprising word that you did not expect, that may generate humor. But sometimes that may confuse you if you don't understand the meaning. So Mad Libs are not actually played this way. Usually the game goes like this. Somebody is like the game master, and then that game master asks people like, give me an adjective, give me a noun, give me a verb, and then they get that whatever the people say, and they just fill in these blanks, and they read the story at the end. That's how it's played, but it's more like a variant that we're using here. We use the context and we try to make the story funny by looking at the context and putting funny words. So these are our contributions. So Mad Libs are copyrighted, so we can't use their books of Mad Libs. We can't use them as our data set and release it. Copyright problem. So we create our own Mad Libs data set, which we call the Fun Libs data set, and we make it publicly available. And we also annotate the data set, like how funny the stories are. We create all these things, and we also have the stories labeled, the words filled in with Amazon Mechanical Turk. So we call people players who fill in the blanks, and we call people judges who grade the funniness of each story. So we release that as well. And then we develop an algorithm called Libitum, which helps humans generate funnier Mad Libs than they can usually generate on their own. So it's not an entirely algorithmic way of solving Mad Libs, it's a computer-aided way. And we also analyze what makes our results humorous. So here is some description of the data set that we released. So we analyzed 50 original Mad Libs. We looked at them, and then we looked at their hint distributions, the words per hint, and like the number of sentences they have. And we tried to create our own stories matching those distributions. And we created 50 fun libs from Wikipedia. Why Wikipedia? Because similar to Mad Libs, Wikipedia articles, they have a title and they have some description of that title, which is very close to the Mad Lib story. So, and also we just so the idea is, like, get the title and the paragraph from Wikipedia, select blank out some words, which we did manually, and try to match those hint distributions and the other distributions. So we have 40 such fun lists for training, and we have 10 for testing. So here is some description. You can see on average you're getting like you're getting like nouns. So it's uh, like roughly there are 7 nouns in one medley, 4 adjectives, and that's our fun list. It's a little bit different, but try to be similar. And here, so like on average, we have like 14.78 blanks per story. They Mad Libs had 16, but they had some other that we're omitting, like person names, like exclamation, like silly word, which we thought were not going to be that interesting. So now, now that we have the dataset level, the next task is to find the judges. So what we do is we make rules that judges will not consider cheap humor as funny. So things like bathroom humor or like fart jokes, like a slang or sexual references. Those are, you don't need much wit to actually create fun that way. So that's not allowed. We need meaningful, funny stories. So this is how we select our judges. So we give 7 Mad Lib like stories to Turkers to grade, and 3 are not funny, just plain Wikipedia articles, and the blanks were there, and then we filled in the words with the original, fill in the blanks with the original words, and then 4 of them were at least a bit funny. That was determined by people in a research group, and so judges grade on a scale of 0 to 3, the integer scale, and then you can see 0 is not funny, 1 is a little bit funny, 2 is more funny, and then 3 is very funny. And then we selected 45 judges that way, based on their performance in that test. And we also select players. So we have 2 sets of experiments, and so first one is with 50 Turkers, each of them filling in 2 different stories. And to reduce some bias, to get some more variety in stories, we create another batch with 2 different stories, and then 30 more Turkers we're supposed to fill them in. And so now we have our judges. What we can do is we can use the judges to find out how good the players are in making stories funny. And so each story was judged by 10 people, and we selected 30 players from those 80 based on their the scores they received. So this is a snapshot of the filling in the blank task. So we had 50 Mad Libs altogether, each of them filled in by 5 players to get some variety. So here is a snapshot. So like you have this, and then you have the yellow blanks that you have to fill in. So for each of these stories, we have 5 different sets of filled in blanks. So for each, here you can have at most 5 different words. And then so the grading task goes as follows: that like you grade the whole filled in story, and then you grade whether each word is funny or not. So this is not funny and this is funny. Okay. And so now that we have this label data set, now we want to create a classifier that can say if the word is funny or not in the context of Mad Lib. So now this is how we label the data set. So funny words are words that receive 6 or more funny votes out of 9. And not funny words are words that receive 3 or fewer funny votes. And so it's more like a vast majority than a majority vote. So like words that receive 4 or 5 funny votes, we don't work with them. So, and if we put those restrictions, then in the training set, so we had 40 training stories. Now we split that into train and validation, and then we have 30 of them now, and 30 times 5, each was labeled by 5 people. So 150 stories, and in total we have 1449 words with rank funny or not. And then we have the validation set. So then we train a random forest classifier to predict whether a word is funny. and so the data set is there. You can go and use it. And so these are the features that we use, right? So the hint type. So like we probably saw that adjectives were generally more funny, so maybe that, and nouns were more funny than verbs, perhaps. So that can be one feature. The word length. Sometimes like longer sounding words, just because they were long, they sounded funny. So we have this language model joint probability, and what's that? So you so given a word that was filled in by Tarkard, we compute the joint probability of the given by the language model, say of the left four and the right four words, including the word, and then we see what's the probability. So, and that's tied to incongruity. If it's highly probable, then that's probably not that funny. But if it's least low probability, then that's a surprising word that may cause some humor. And then we have this joint probability relative position. So the joint probability is just a raw number. So the relative position is maybe like a so you have all the words you have all the words in the for the blank. You can get that from the language model, and you can see uh, where that word would place. Like, is it like a very like top probability word or like a bottom low probability word? So that's a number from 0 to 1. And the letter trigram probability is the min, max, and average, and that is like so some words are just inherently sounding funny. So like if you use fighting versus whacking, which is more like a synonym, but just because it sounds different, so we thought these letter trigram probabilities will help us find those funny sounding words. And then we have the similarity to the title, story, and the sentence, which we use using the Glove word vector. So we so that word we see how similar it is, how its distance from the title, and then the story, and then the sentence containing the word. So now this is the results from the classifier. So it was a random forest. And so you can see our precision like 70%, recall is roughly above 80%, and then F score is like 75% or more. And the accuracy on the training set is 72%, and then we have almost like 70% accuracy on the validation set. So given a word, whether it's funny or not. And then so these are the features, the importance that we computed. And so these don't tell directions, these just tell like these were the important features. Sentence similarity is coming up as most important, and then you can see the other ones. So now let's compare to some baselines. So this is the chance baseline, which is just predicting the most frequent label in the data set. So, and then that gives you 57% or 54% accuracy on the validation set. And then this is another baseline chance hint. So we look at each hint and we see what is the majority. Is it like funny or not? And then if we predict that way, we're getting something like 59% accuracy. And then this is linear SVM using 3 features, which were the title, story, and sentence. And that's like 60% accuracy. What's interesting here is, so you can see the SVM weights tell you that, so the words should be similar to the title and not similar to the story or the sentence. Maybe that generates humor. Maybe that has something to do with incongruity. If you put in words that are similar to the title, so maybe that has some kind of meaning for the title and just doesn't fall into the sentence nicely. So you can say our accuracy is better than these baselines, but still lots of room to improve. And so now we have, so yes.
Can you explain like how to generate the chart on the top right?
So this is so you have trained a random forest, right? And you can compute the feature importance, how important was each feature in the classification. And I'm not going to get into the details, but it's based on, like, it's based on splitting nodes when you create the forest, and how much impact a feature has in deciding whether to split or not. I think that's the idea. So, but it doesn't tell you, like, is it like positively correlated or negatively correlated. Okay. So now we have our classifier. So we want to test how different systems perform. So we have three different approaches for filling in Mad Libs. One is free text, which is players just fill in the blanks and without any restriction. And then this is LMC, which is language model plus multiple choice. So here, for each blank, we use a language model to generate candidate words that fit the hint type. Okay? And we keep top 20 words according to that language model joint probability. And we use humans to decide which candidates to fill in blank. So you have, it's more like a multiple choice. You have for each blank 20 choices based on how probable those words are. And then so the idea is, like those words would fit the context, and maybe one of them will be funny and human will be able to identify that. And then this is the Libitum model that is similar. So it's again using the language model to generate a list of candidate words. Now we rank them all using our classifier, right? So we keep the top 20 funny words as ranked by our classifier. So say the language model generates 500 words. We put each word in that context, and we check using our classifier, like what's the score it's getting for funniness, and then we rank, and then we select the top 20. And then we again use humans to decide how funny the word and the story to find out funny words. Okay. So now, so we had 10 test stories, and here are the results from the three different formats. So for each approach, each of the three approaches, we have each story filled in by three different players, and then we have each of those stories graded by 9 judges. And so here are the grades that they received. So you can see that LMC is doing bad, right? It's more towards like 0 and 1. And it's really difficult to find out stories that are funny, just, like suggesting words that go in the blank more with high probability, and then letting humans choose. And this free text, so humans had no restrictions, so they're doing much better than here. But they're not doing that better than this case, right? And so yeah, and you can see the mean funniness score, like out of 3, is 1.51, which is better than the other ones. So, and here's a visualization of the results. So for each of those 10 test stories, I have the three grades by the three mean grades for the three different filled-in versions. And you can see this is Libitum, and then the green is free text. So what we can say is, so you can see, like the best 2 funny stories were actually from free text. So it tells you that given no restrictions, humans can actually do much better than like those restricted and multiple choice cases. So, and this Batman story was really funny, and I think we'll come back to it later. And also we used a fully automated system just to see and expect some bad results. So, which is just, like you have the ranked words from Libitum, you put the top, like most funny word, and then you check the performance, and then the mean funniness grade was 0.8, which is worse than all of this. And that makes sense, because those words may just not even belong to the, like you don't take the context into account that much. So you don't, maybe some of them don't have even some meaning. So here are some excerpts. So this is one Mad Lib, and so this is from one of the 3 versions. So beauty contest is a or observational contest to decide which organism is the most flammable. And then you have a beauty contest is an elaborate contest to decide which brawler is the most deadly. The bold-faced words are the one that received 9 out of 9 funniness votes. So they really sounded funny to the judges. Now, want to make something more interesting. Can anybody guess whether the first one is from where the first one is from or the second one is from? Any idea? Or how many of you think the first one is from Libitum? No? Is it like stretching or raising your hand? You think so? And first one is like free text using humans. And second one is free text or Libitum. Okay, I think nobody has any clue. So the first one is from Libitum. The second one is from free text. And what cheeky thing you can use to identify maybe whether it's from free text or Libitum is you see that these two words they are directly related, and that's what you get. You have unrestricted filling in the blanks, right? So that's where humans are really good at. So when you have like something like which blank is the most blank, they're directly related, and humans can put two words nicely and get much more humor. Whereas this just like looks at this much context and then predicts a word, and looks at maybe this much context and then predicts a word. So you don't capture that connection between those words. So I'll skip this one. So we did some correlation analysis. So I was telling you that the incongruity theory of humor, that unexpected or surprising word can generate humor. And we also asked judges how coherent and meaningful those stories were. So they judge for each story whether it's like 0, 1, 2, 3 again, like crazy and disconnected, the story has no meaning, somewhat makes sense and hangs together well, and then almost totally coherent. So, and then here are those correlation results. So you can see the incongruity. So this is saying, did incongruity create humor? And like, so a lot of them, it's really highly positive correlation, and the bold-faced ones mean there. We use the t-test to verify statistical significance. And so you can see again here, coherence was important, but not this one, right? Here, just the language model suggesting the words, somehow they were choosing the words. Say you have like 15 words per story, and people are choosing words, but they can't make a funny, coherent story for some reason. And so here is one such story. So this was the best Batman story. So green words are from free text, the red LM10 and the blue Libitum. So want you to notice the green ones. Look how the story goes. So Batman is a fictional character and one of the most obese superheroes. Batman began in comic books and he was later liposuction in several movies, right? Batman lives in the edible city of Gotham. So, and like it goes on. So it paints the picture that Batman is not whatever he is, he's more like obsessed with food and eating, and that's all his intention is, and that's the domain of words it uses to map, and then like to make this story fun. It's so consistent, and it continues the story, and that's difficult to do using Libitum. And so you look at the whole context, and it's really amazing how do they do that. So like this was also again. So look at the Libitum one. So Batman's one of the most inefficient superheroes, and he was later imprisoned. So they don't like they don't go together that well, the words, but like, so for example, as an adult he wore a costume, he wore a veil to protect his jaw while fighting acne in Gotham. So these are like local humor, right? These are more like the incongruity playing here. So this is just local humor that's happening, but then you don't have the flow and you don't have the connection. So, and that I think is really interesting. So yeah, and that's pretty much the work. And so let's summarize what we did. So we released a new benchmark for computational humor research, and we have a data set of fun libs and their filled in words and then their funniness grades. We developed an algorithm called Libitum that can rank blank filling words by funniness. and we compared the advantages and disadvantages of these three approaches for filling in Mad Libs. And overall, we see that the computer-aided libitum approach outperforms the human-only approach, and some humans generate humor word using words that are funny and coherent, which is difficult to achieve using libitum. So, and that's it. Anybody has anything to ask?
Go back to the slide where you had the it's like the ranking of weights for the various features of the blue bars on the upper right.
Right.
So in the lower right, I'm correct with this. So your linear SVM with your three features, which is just title, story, and sentence similarity, they got that ranking. So basically, if we just take the absolute out of the importance, I thought title was important, less story was slightly less so, and sentence was not important, right, for making this determination. But if I'm reading this right, that's like the opposite ordering of those three that we see in the upper right.
Yeah. Right. So,
well, but if it's negative, it's important. Right?
Yeah, that's what I'm.
No, but I mean, he's saying the magnitude, right?
Magnitude, yeah. Like
absolutely.
Rank by magnitude is title, story, sentence
Right.
versus sentence, story, title.
Yeah.
Those are reversed.
So firstly here, like we decided these features looking at this list and picking the top three. So we thought they would be important. Now,
Okay.
And so what you get here, you have the other features that are coming into play, right? And those other features may be helpful in determining whether it's 0 or 1, which you don't get here.
Yeah,
Right.
So I understand theoretically why they can be different. I just thought it was interesting that they are like.
Yeah. That is interesting, right? I mean, what I'm getting from here is telling me that I need to put in words that are somewhat similar to the title that probably has some meaning, like if it's like zebra, I don't want to talk about like MacBook. And, and then I want to deviate from the local meaning in the sentence. So that's what's generating the surprise. That's what I got from there.
Yeah. Because it's like the negative weights. That's like incongruity.
Right.
Yeah. I'm just not sure why the reverse.
Right. Anybody? Anything else?
How did you choose to go with random forest and not?
Oh. We tried a bunch of other models. We even tried doing linear regression, right? So you have these votes like 0 to 9, words will receive 1, 2, 3, 4, 5, 6, 7, 8, 9. With just doing this preliminary test, we weren't getting better results, and we thought that like trees and random forests, it's the way they split. Like if you can do things like so this word is similar to the title, but not the sentence, and it has, like the average letter probability is low. Maybe you combine them, and then that creates humor. So we thought, like maybe the results will be better if we think of it that way. But I mean, we tried out a bunch of different cases, and this came up as the best result. Yes.
You were saying that humans are funniest because they chose one topic and all the fill in the blanks were from related to like food or something like all the Mad Libs had something to do with each other.
Could be, yes. That's one of the reasons, right?
So the funniest examples you were
Right.
saying
I mean, the funniest, which one? I mean, we were visiting the Batman one, right? And that was the funniest vote. And that's what happened there. I mean, we saw that pattern happening there, right? So that was one of the tools that we saw humans using. But just this, like just this having no restriction, that you can put anything you want, right? You're not constrained, and that allows you to, like in many cases humans will outperform because you're not restricted, and you can just go into a totally non-funny direction, but you can also go into a much more funnier direction than if you were constrained by those choices. So yeah, well, I guess.
So I have a question.
So you do this while you're at Microsoft.
Yeah.
Why are they interested in that?
So they're interested in AI. They're interested in humor. So and maybe it has something to do with Cortana and humor. So some ideas, and I'm gonna leave it over there. So yeah, they think maybe it's time that Cortana makes jokes, makes interesting conversations, and maybe this is one step. Okay, so I think that's it then.
Oh yeah, can you guys sign in real quick?